Okay. Okay, so for our first class, we are for biochemistry, even my general microbiology or food chemistry, we all go over basic knowledge of chemistry. Okay, so the topic will be introduction of chemicals or chemistry. So the first question, if I wrote C612, do you still remember what that means? Okay, this is carbon. You all know this. A backbone of all a biological significance chemicals. What is 6 means? That is an atom number. Or we say atomic number. What is 12 means? Mass number. Or we say mass weight number. And sometimes we call it molecular weight. Okay, if you still remember those, which means you're good at chemistry, pretty good. Some of you may forgot. Therefore, we have our first question. We talk about atom. Okay, what is atom? Very simple. Right in the middle, you have a center. The center is composed by proton, P-R-O-T-O-N, and the neutron, N-E-O-E-U-T-R-O-N. Okay, they're surrounded by what? A very heavy cloud. This is called electron clouds. This is the basic structure of an atom. Now, what do these things mean? What does proton means? What's a protonic number? Should be, sorry. Protonic number. What does a protonic number means? Which means what type of atom it is. What does a neutron means? Which means it could be an isotope. Now what's the electron indicates? Electron indicates ions. Okay, let's talk about the atom first. What are the major atoms for a biological significant chemical in our body? Hydrogen, proton. What are the second one?
Carbon.
Carbon, oxygen. Is it right? What are others?
Nitrogen.
Nitrogen, sulfur, and phosphate. Okay. What is the atomic number? What is the mass weight? Or mass weight number? Let's do just a review. 1, 6, 8, 7, 16, and 15. Now, what is the mass weight number? That's a protonic number add with neutron number. Okay, what is this one? This is 1, is that right? Because for hydrogen, there is no neutron. What is carbon? 12. Oxygen, 6. Nitrogen, 14. Sulfur, 32. Phosphate, 31. Because this is 15, proton number, and 16. Okay, next question, what is the percentage? In our body, let's say in a bacteria, hydrogen is a lot, 49%. Carbon, around 25%. How about oxygen?
25.
Yeah. And I tell you one thing, HCO, those three alone is 99% for our whole body of a bacterial cell or a biological significant system. How about these? Nitrogen 0.5%, very low. Sulfur 0.4. How about phosphate 0.1? So these three add up together is 1%. They'll add up is 100%. But I want to tell you one thing, it's not going to be 100% exactly. The reason is we have ions here. Okay, what are the ions' significance in the body? Sodium, potassium, calcium, and iron. It could be 2 charge or 3 charge. What else? Sulfide, phosphate, chloride, and some others. These about 1% dry weight of a bacterial cell. These are together composed by the major chemicals in a bacterial cell. Okay? So that's why I'm telling you these are something we want to go over. What's the isotope? Hydrogen originally is 1, is that right? It could be 3. That's use a little bit of radiation activity for testing DNA and RNA in some of the bacterial cells. They use it. And could be 15, is that right? Do you remember when we talk about genetics? Maselson and Starr research, they're using N15 to verify semi-conservative replication during the DNA replication process. You know iodine 125? Iodine should supposed to be what? Iodine 121. Iodine 125 is using for radio immune assay. That's called RIA, and this method back in 20-30 years ago is very popular to testing all the hormones in the blood cell. Okay, so these are the things we talk about that. Now we want to spend some time talk about this electron. This is going to be the huge. So our second question. We will talk about the electron arrangement out layer of atoms. And we want to talk about those. Okay. I had a center is proton and a neutron. You already knows about this. So the next question, how the electron going to be arranged? This is not on the slides, but I hope you know. You may learn in your chemistry class, may not learn, you may forget. A little bit tricky, but I want to explain to you, and you should know about that. So how they arranged them? Their arrangement basically is from inside to the outside layer of an atom. And there is a multiple layer could be. Each number, 1, 2, 3, 4, 5, could be go 9. And then we have an English letter to represent that is K, L, M, N, O, da, 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 da. So the first thing you need to know, the electron arrangement basically is from low energy close to the proton and the neutron, and this is also we call it a nuclear center. From the low energy, go outside is from high energy. Basically, arranged like that. However, you should know, sometimes the jump will happen. Okay? This is the number one. Then the question will be, how they really arranged? Now this is gonna become tricky. Each of these layers, let's say number one, number two, number three, number four. I'll just give you some example. They will exist as sublayer. And those sublayers composed by orbitals to hold on and occupied by electrons. Now how we determine that? We give N is the energy layer number, and L is the shape of orbitals. Now what is the formula for that? The formula is L less equal than N minus 1. Okay, therefore we have the questions for you. Let's say the N equals 1. Then the L will be 0 only. What's the shape of the sublayer of the orbital? Circle, sphere. Not only one direction. If the N equals 2, then the L could be 0 and the L could be 1. Then what's going to be the shape? Could be sphere, then that means S, okay? That means S. It could be something like a dumbbell. This is called a P. Because it's like a dumbbell, therefore the expansion direction could have 3 different directions. It could be just perpendicular, we call it y-axis. It could be flat, horizontally, we call it x-axis direction. And it also could be a little bit curved straight. This is z-axis. So 3 different directions. This is only 1. This you have 3. Okay. How about the N equals 3? You can do the math. The L equals 0, L could be 1, L could be 2, therefore comes out with what? This one, I will say, looks like this type of shape. This is called d orbital. And d orbital has 5 extended directions. So I'm not going to draw it. Now how about N equals 4? Then the L could be 0, L could be 1, L could be 2, L could be 3. what happened? This will be F orbital. Have 7 extended directions. We're not going to draw this. Okay? This is some of the basic knowledge before we talk anything further. So we have these basic knowledge, then let's go. Now the question is, how the electron going to be arranged? So you have to follow 3 rules. Okay, this is 3 rules. Rule number 1. I already mentioned them. Called the minimal energy policy. What that means? Arrangement of the electron basically from inner to outer, from low energy to high energy. Filled with the inner layer first. This rule number 1 is very simple. Rule number 2. Pauli exclusion policy. What this means? Pauli exclusion policy means every single sub-layer orbital can be maximally occupied by 2 electrons. And the electron can spin, you know that, up and down, and spin opposite direction. So basically, if you understand it, let's say this is 1s. This is 1s orbital sublayer. What's going to be? Up and down. Spin opposite direction. Maximum can only hold on 2. Occupied by 2. Rule number 3. Hans rule. What is that? Okay. Sublayer orbital first singly occupied by electron. And these electrons spin same direction before doubly occupied. So what that means, give me an example. This is 2p, for example. 2p layer. How they do it? They first occupy all these. 2p layer has 3 orbitals. Electron goes there first. They fill it up first and spin the same direction. Then have the second one go there. Every corner, every circle, every box orbital can only occupy the maximum by 2 and spin opposite direction. So this is follow Pauli exclusion policy. Now, by the way, Pauli is American chemist. Hans is a German chemist. This is back in 10s or 20s. They established these rules. Okay? Now, I'm talking about so many, it looks like it's It's very confusing, seems like. Let's give some example, okay? So let's give some example. How about carbon? What's going to be the carbon, the electron arrangement? So we're going to draw the box first, okay? This is 1s, 2s, and 2p. How we do it? Up, down, up, down, up, and up. So what's the arrangement? 1s2, 2s2, and 2p2. Now there is a question. Why this one is not in here? Because have to follow Hund's rules. Okay? Second example. Let's do nitrogen. Okay, what's going to be the nitrogen looks like? What going to be the nitrogen looks like? 1s, 2s, 2p. So up, down, go up, and up. So 1s2, 2s2, and 2p3. Okay, how about oxygen? That's very important. We have to talk about that. How about oxygen? Still the same thing, we draw the box. Okay, 1s, 2s, 2p. Up, down, go up, go up, go up. How about this guy? The last one. Is that right? Because this is follow Pauli exclusion policy. Therefore, 1s2, 2s2, and 2p4. Okay, you can go ahead to do a difficult one. How about phosphates? You want to do that? You can do it. Okay, let's do it real quick to the phosphates. Okay. You can challenge by yourself a little bit difficult. Go here, this one, and we have this guy right here. So 1s, 2s, 2p, it's gonna fill up everything. Go down, go up, go down, go up, up, then go down, go down, go down. So 1s2, 2s2, 2p4, that's 8. So this is 3s2. Go up, down, then go here. What are you gonna have? It's gonna be 3p. Up, down, and down. That's going to be 5. Okay, that's phosphates. So that's what you do. So I have to move the camera there because it's already full. Now, the question will be, sorry. Let it go here. It's got to be 6. So the last one. 2p6. Okay. Oh yeah. Sorry. That's 16. Is that right? Is that going to be 6?
No, she's saying the 2p4 should be 2p6.
Oh, sorry. Yeah, that's 2p6. Sorry. Then that's wrong. Sorry about this. I messed up this. So that's 10. And go here will be up. So 3p 3. Is that right? Okay. Yeah, thank you for fixing it. Okay. Now I'm gonna tell you one thing. Basically you follow it. Is that right? You understand it? How about potassium? Then this is gonna be tricky. This is 19. Okay, we can do one more thing. Let's try it again, okay? We have found these things. We can try it again. Go here. So we had this 1s, 2s, 2p. We're going to have 3. Okay. Then we go 3s and 3p. Okay, what we do? Up, down, up, down. Fill up everything, then go up, down, up, down, up, down. So that's 1s2, 2s2, 2p6, 3s2, 3p6. We add up together, what is that? 18, is that right? Do you think here gonna be 3D? Based on right here, it's gonna be 3D, is that right? No, it's not. It is what? It is 4s1. So certainly it's jumped. Here happened is electron jumping. Now, how do you know about that? This is because people are using the advanced spectrometer tool to do the observation of the electron arrangement. And then they find the potassium is not really strictly follow those three rules. Okay? So this is what I go a little bit deep, go over some atomic chemistry for your understanding. Now, how are you going to calculate all these energies? Then that's atomic physics. It's more complicated. We're not going to go there. I haven't touched physics for like 25 years probably. So we're going to finish. We're going to almost done here. Now, there's some of the conclusion you should know. For a biological significant, because we all talk about the biology or the other things. Biological significant chemical. Okay, always it's atom. There usually the outer layer is 8 electrons. This is we call it octet rules. That is important to know. It's almost 8. We don't care about the so large one, okay? Now another question. You're gonna ask me, why are we gonna spend the time and talk about these? It's so confusing, seems like. Because we all care about these outer layer electrons, especially in the really outside. Those we call it a valence electron. Why? Why it is important? Because they're gonna react it with other atoms to form biological and chemical bonds. Therefore, we end up with 3 very famous common chemical bonds. If you still remember, number 1, Ionic bonds. What is Ionic bonds? Do you remember the simplest one? Calcium chloride.
Sodium chloride?
Oh, sorry, sodium chloride. Sorry, sodium chloride. So simple. How they connected with each other? Sodium is positively charged. Chloride is negatively charged. So they attracted with each other, is that right? Why? Because sodium, they lose 1 electron, and the chloride is gain 1 electron. So this guy, we call it cation. And this guy, we call it anions. So ionic bonds is basically cations and anions attracted with each other. Now, is this a strong bond? No, it's relatively weak. Not very strong. But in a real life, it's very, I would say, tough structure. Because it will form in crystal. Is that right? So we say it's a crystallization, LATTIC, lattice. If you want to break down them, you definitely need to break down the lattice energy. Okay? Now, how they really composed? The electron is right here, and this is donate 1. And this whole thing, we call it Lewis structure. So that's ionic bonds. Now, I'll give you an example later on for ionic bonds. It is important. It is really important. Using in the food industry for electrolyzed water. Electrolyzed water, if we're using food grades, it could be with electricity. It will become sodium hypochlorite and hypochloric acids. So one is a sanitizer, another one is antimicrobials. Or we say one is a cleaner, another one is antimicrobials. We'll talk in our lecture 3, talk about water. So I just want to give to you the ionic bonds, the first one. Second one is covalent bond. Covalent bonds is relatively a very strong bond. It's a strong one. It is basically the two atoms, they share electron. Okay. What a good example? A good example is water. The water is so simple, H2O, everybody knows that what is going to be looks like. This O will be in the center, connected by H. And people find this O usually, although it's shared with hydrogen atoms with electron, but it showed a little bit strong attraction. So we use delta negative right here. And these two protons, we put delta positive. Therefore, it comes out with a concept called electron negativity. The electron negativity is a value. Basically, you can look at your textbook, is H, C, N, and O. They are decreased from this direction. O is about 3.5, N 3.0, C 2.5, H 2.1. Because of they have a different electron negativity, so even they have a covalent bond, so say that they are sharing, but they are more attracted for electron compared to the other. Especially in our bacteria or in our biological significant chemicals. These two usually play an important role. Therefore, we come out with another thing, have two different types of the covalent bonds, which is nonpolar and polar. So what are the nonpolar means? If the connection is CH, HH, and CC, now basically they are same electron negativity, which means they attract electron are very similar. We want to mention this later on. Okay, why you see the difference here, but why it is still we think it's very close? Because the electron number is close, and also there's a hybrids for the electron arrangement there. So that's why we want to mention real quick. Now, what means a polar? Polar, which means if you have a higher electron negativity chemical with a lower electron negativity chemical. So let's say OH, ON, CH, OOM, CN, and CO. And therefore, you come out from the different electron negativity attraction. So there you have a polar covalent bonds. And this is very important. Why? Because of the polar characteristics of a water, then we will say this water is a good solvent for dissolve most of the chemicals. Okay? Now let's talk about this guy a little bit, since we talk about here. So the CH combination If the CH combination, we say it's an organic chemical. Now, otherwise, we call it an inorganic chemical. But how they really combine together? We give you a very easy example, CH4. This is a method. So when they combine together, if we want to draw it, this is basically the carbon. These are carbon. This is spelled. And these is actually is H. They'll combine like this. Now why they can do like that? Because they can do some type of the hybrid. If they combine together, usually we draw up a little bit. We mentioned about the C12, C612, the arrangement is 1, 2, 1s2, 2s2, 2p2. So, in the 2s, there is 2 electrons. So 2s2. And right here, we call it 2p2. Is that right? So we have up and up. These two orbitals can do a good job. We call it a hybrid. They could be combined. They finally become what? Become everything is up, 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 and this one is golden. So once you combine this is called sp3 hybrid. Now, why the sp3 hybrid is important? Because they will form a called tetrahedral tetrahedral arrangement. When they become a tetrahedral arrangement, these will actually forming a theta angle. And this theta angle is about 1.9.5 degree. And the people also find that this tetrahedral arrangement is same for water molecule. Because for every water molecule, they are surrounded by H, H, and by another H. And this angle is 104 degrees Celsius, a degree. Okay? So, the water molecule is also tetrahedral arrangement. Once it's freeze, which means the temperature decreased, it will become a hexagonal halo structure. This is what means for ice. Therefore, the ice, the low density, they can float it on the water surface. Okay, so this is we gave you something to talk about that covalent bonds. Covalent bonds is very strong. Now, by the way, we mentioned about electron negativity. We mentioned about the electron hybrids arrangement. Who is the person mentioned about that? This is the American scientist called Pauling. In 1931, he pointed out the hybrid, the electron hybrid arrangements. He got 2-time Nobel Prize, 1952 for chemistry. This is everybody knows. Then people think he got another chemistry in 1962. In 1952, he got a chemistry Nobel Prize. In 1962, he won a Nobel Prize of Peace. Why? Those are the chemistry person is a very smart person, the same as Albert Einstein. and Watson and Crick when they find the DNA double helix. And just after the Korean War in 1950s, there's still lots of people wanting using a nuclear weapon. And then sign the petition, go to President Eisenhower, and the petition also go to the UN, United Nations. They strongly opposed to use nuclear weapon during the war. So that's why he was one of them to be awarded the 1962 Nobel Peace Prize. Okay, so there's the story behind it, but he is a great scientist and a chemist. And I also want to mention, he almost get to find the DNA double helix, but not cross the finishing line. It's Watson and Crick, they find the double helix. So in the history, we will mention him again. He finds the alpha helix of the DNA, of the protein secondary structure. We will mention real quick again, okay? So that's we go a little bit off for talk about covalent bonds. The last one is the hydrogen bonds. Okay, the hydrogen bonds is very weak one. This is not a strong chemical bond. What are they? I'll give you an example. We just talked about the water molecule, is that right? Okay, I have another water molecule. How the two water molecules connected? That's hydrogen bonds. How about here? This is covalent bonds. How hydrogen bonds is very easy to break down. That's the reason water can move in. This is so easy to break down, and this is hard to break down. That's why how we break down the water, going through electricity. Is that right? Breakdown become oxygen and hydrogen. So that's a good example for covalent bonds and hydrogen bonds. Another thing I want to mention is we always going to mention the energy. What's the energy for hydrogen bonds? It's very low. It's about 5 cal per mole. How about the covalent bonds? Up to 110 cal per mole. That's a very strong one. Now, another example for hydrogen bonds, if you still remember. Do you remember DNA double helix? A complemented with T. Adenine complemented with thymine. Cytosine complemented with guanine. What are these? Hydrogen bonds. Is that so weak they can separate? That's why the DNA is doing the semi-conservative replication. Now, basically, what is the hydrogen bonds? Is the bonds connected between proton atoms and another atom, let's say is oxygen. This atom usually have relatively strong electron negativity. Okay, so but basically it's weak. Okay, so we finished to talk about these chemical structure and the bonds. Now we want to go ahead to tell you what are the major chemical structure we're going to mention in the classroom. I hope everybody going to get there. Our major chemical bonds. What are the major chemical bonds? What is this guy? Meso. Okay, this is the first one. What is this one? Hydroxy. Where the hydroxy always happen?
The base.
Yeah, the base. 5 carbon, OH. This guy is always missing. Is that right? And I give you another example. amino acids. We call it CH2OH. What's that? Sorry. That's a polar amino acids, but non-charged because of this guy. Okay, hydroxy. Okay, we mentioned about here things. What is this one called? Carboxy. How about this guy? Amino group. Okay, what else are we going to talk? What is this one? Keto. We will mention keto-CME during the Maillard reaction. So that's keto. How about this guy? Aldehyde. A very good example. CHO, CHOH, CHOOP. What is this one? Glyceraldehyde 3-phosphates. Is that right? Aldehyde. What else are we going to talk? How about this guy? SH. That's called sulfurhydro. So easy. What's that? Again, do you remember this amino acid? We'll go over all of them, okay? What is it? What's the name of this one? Cysteine. Have a sulfur. Cysteine basically can connect to become a sulfur bonds. What are the last one we're missing? What is this one? Phosphates.